So in this lesson, we're going to start looking at the differential equations for an RC circuit, kind of talk about how these equations actually work. I think in some ways talking about the differential equation is pretty useful or pretty convenient because it gives us other ways to kind of describe. I'm going to start with the discharging capacitor first. So we have a capacitor that is fully charged initially and it is connected in series with a resistor. What happens is your current is maximum to start with. Your current decreases as the charge on the capacitor decreases. This is because the potential drop across the capacitor and across the resistor have to be the same. As one decreases, the other decreases. So the first thing I would do is rewrite this in terms of Kirchhoff's loop rules. And if you write this in terms of Kirchhoff's loop rules, you would get Q over C plus IR equals 0. Basically what that says is the potential drop across the capacitor plus that across the resistor, those two values add up to be 0. Now if I plug in what I really is the time derivative of charge, dq dt. So if we had a function of q that we knew was a function of t, I is really the first derivative of that function. Now if I take and solve this thing for q, I end up with an equation like this, that dq dt times r equals negative q divided by c. Or we could say negative dq times dt times r equals q over c. And if we rearrange this one step further, I get dq over q equals dt, or negative dt over rc. So get all the q's on one side and everything without a q on the other side. In calculus, when we do integration, I actually call this separation of variables. In this technique, get all of one type of variable on one side and all of another type of variable on the other side. It's a way to deal with a problem like this that has a rate within the problem. In this case, we had dq dt as a function of q. Now I can integrate both sides. The right-hand side is really easy to integrate because dt over rc just becomes t over rc. The left-hand side, a little bit harder to integrate, but not all that much. If you have dx over x, that's just natural logarithm of x. Now you notice I put a plus c on the right-hand side. We'll talk about that in a second. The way to get rid of natural logarithm, to get the function out of this, is take e to the both sides. And so you get e to the negative t over rc plus e to the c power, really. Well, remember, when you add exponents, it's like multiplying numbers together. And so really we say this e to the c is just some constant c. We don't really know what it is. But we can say that that constant is the initial charge on the capacitor. So here we have a function of charge on the capacitor that's related to RC, that time constant, time t, and the initial charge of the capacitor. It's worth pointing out that this is an exponential decay function. One thing to point out about differential equations, if you ever get a derivative of a function is equal to negative of that function, that is always, always, always exponential decay. The solution looks exactly the same. Some other places where you see this, if you go into, say, chemistry is a good example, something like radioactivity. Radioactive decay happens to be this exact same type of mathematical system. So the second one I want to do is a little bit harder, and it's a little bit harder because we have a few more terms that we have to deal with. And this is a differential equation for charging a capacitor. So here I have a switch S, and there's a battery, a resistor, and a capacitor all in series. I'm going to flip the switch. The current is maximum to begin with because the charge on the capacitor is 0. But as the charge on the capacitor builds up, the voltage on the capacitor gets bigger, the voltage on the resistor gets smaller, and eventually we fully charge the capacitor. So if we write out what that looks like in terms of Kirchhoff's rules, we could say V minus I times R minus Q divided by C equals 0. Basically, I times R plus Q divided by C should equal the voltage of the battery at any point in time. So we plug in the definition of I. There we get our dq over dt. And now we have to do a little bit of algebra to do the separation of variables in this case. The way that I did that was I divided everything by R first and added the dq over dt to the other side. And so I get something that looks like this as my result. Now on the left-hand side, I'm going to combine these two fractions. Find the common denominator, which would be r times c. In order to do that, I need to multiply the left-hand fraction by c over c, and so I get v times c, which ultimately is the maximum charge of the capacitor, minus q, divided by rc is equal to dq over dt. At this point, I'm going to pull the negative sign out, and the reason for pulling the negative sign out is it makes the signs and things work out better when we actually do the math, or when we actually do the calculus. If you're trying to take the integral of negative q, you have to have a negative sign that pops out of there. This takes care of that for us. And then I'm going to separate my variables, divide everything by q minus vc, move the dt to the other side, and now I'm going to integrate both sides. The left-hand side is a pretty easy one. It actually looks exactly the same. The right-hand side, when I integrate from 0, which is the starting charge, to q, really q max, the maximum charge, we get this function here. You get ln of q minus vc minus the ln of vc. So what I'm going to do is I'm going to combine those, because in a natural logarithm like this, you can, if you have natural logarithm of something minus natural logarithm of something else, it's basically natural logarithm of the something divided by the something else. I'm going to take e to the both sides to get that over there. And then I do a little bit of algebraic manipulation to make this work a little bit better. What I'm going to do is multiply by vc. And then if I add a vc over to the other side, I can pull vc out. And so I get v times c times 1 minus e negative trc equals q, where vc is really your maximum charge. It's worth pointing out that this looks like, I actually call this a logistic function. It's something that will ultimately, if t goes to infinity, work out to an asymptote. In this case, that asymptote is v times c, and its maximum is when t is equal to 0. So let's do a quick problem dealing with these concepts. And the quick problem that I have deals with this circuit here. Looks kind of similar to the circuit we had before, but a little bit different. We have a 50-volt battery. There's a switch in here. That battery is connected to the switch and then to the 50 kilo ohm resistor. From the 50 kilo ohm resistor, there are two paths. One goes through the 100 kilo ohm resistor, and the other goes through the 500 microfarad capacitor. So when I turn switch S, I want to know three things. What are the initial currents through both R1 and R2? What is the steady state current through both R1 and R2? And then what is the maximum charge stored on the capacitor? So when we talk about steady state current, what we're really talking about is if I flip this switch and I've allowed the capacitor to become fully charged, what happens? So you can think about what happens if t goes to infinity as the good example of this. So let's think about the initial currents first. I flip the switch. What happens is if I look at path through R1 versus the path through the capacitor, this path is 100 kilo ohms of resistance. This path going around this way initially, since there's no charge stored in the capacitor, effectively has 0 resistance. Now if we think about this, how I know electricity works is current tries to take the path of least resistance. If one path is 0 and the other one is 100,000, well, the current is pretty much going to take the path of 0 to begin with. So the initial current through R1 is actually 0, because all of the charged particles are going to move through the capacitor the moment that switch is flipped. Now, as the charge builds up on the capacitor, V for the capacitor increases, so V for R1 also increases, and so we'll eventually end up at a place where there is current through R1, and the current through R1 is changing. So effectively what this circuit really looks like is this. Well, I can figure out the current through the 50 kilo ohm resistor. V equals IR, 50 divided by 50,000 equals 1 milliamp. So that's the amount of current through the second resistor. Now what happens when we get to the steady state? Well, in the steady state, that means that the capacitors become fully charged. So we need to figure out what does the circuit kind of look like when the capacitor becomes fully charged. Well, I want to really figure out what the equivalent resistance of this circuit is. If the capacitor is fully charged, effectively no current is going to be going through the capacitor. So really what we have in this case is two resistors in series. all the current is going to go through R2, and all the current is going to go through R1. Because the capacitor is fully charged, there's going to be no current that's going through that at that point in time. So the equivalent resistance is really 150,000 ohms. So my steady state current for both R1 and R2 is 0.333 milliamps. Now, if you don't believe me on this problem here, we could actually set up this circuit and measure the currents and prove that this is the case. It actually happens to be a little bit easier to measure voltages than currents because 0.333 milliamps is a really small current. But I'll guarantee you that this works. I've tried it with the circuit just to prove that it worked. Now the last step, what is the maximum charge stored in the capacitor? Well, I probably want to figure out what V across the capacitor is. Well, since the capacitor and R1 are in series with one another, if I find the voltage on R1, I know the voltage on C. So if I plug in that 0.333 milliamps and multiply by 100,000 kiloohms, I get 33.3 volts. Well, Q equals C times V. I just take the value of C, multiply by the value of V, and I get 16.7 millicoulombs is the charge on that capacitor. So let's get a quick overview of a problem that is a little bit more complex because there's more things going on in that problem than your straight up simple RC circuit type problem. So that kind of wraps up our unit on circuits. When we get back, our next lesson, we'll start looking at magnetic fields and magnetic forces and how does magnetic field or magnets start to play a role in what's going on with current or charged particles. What we'll ultimately get to is a situation where changing magnetic fields can create currents, and current can create a magnetic field. That's our ultimate goal, what we call induction. It's actually really, really cool. And the end result of that goal is a set of equations called Maxwell's equations, which basically relates all electromagnetic phenomenon in a set of 4 very compact and neat equations. One of, I would say, the cornerstones of modern physics and probably one of the greatest achievements probably in about the last 200 years in terms of physics.